Welcome to Clouds and Swarm at the Edge by Pratexo, the edge computing plug and play platform as a service that lets you unlock the value of AI and IoT. I'm Blaine Matthew, the CEO of Pratexo. Good to meet you all today. The star of the show, though, is Petter Graff, our CTO, and he's going to talk a little bit more about himself in just a second. But before we get into that, let's talk about some of the logistics here. The idea was to make this one a little more interactive than your standard webinar. So the goal is not just to listen to slides for 50 minutes and then maybe answer a couple of questions at the end. But Petter is a very interesting speaker and engaging teacher. He actually teaches on a lot of these topics as well at various companies and universities. And we'd love to make this interactive. So two ways we can do that. First of all, if you've got a question at any point in time during the presentation, you can click the raise hand button that's in your screen. It'll pop up on my screen, and then I can unlock your ability to speak via voice to Petter, all right? So what I'll do is I'll say, Hugh's raised his hand to talk, Petter. Let's let him ask a question, and then Hugh, you can go ahead and verbally ask your question to Petter. That would be really cool if we can have some good old-fashioned verbal back and forth. For those that would prefer to do it via the Q&A chat, we can do that as well. Type your question into the Q&A box, and I will get to it either during the presentation or at the end, depending on what the question is. All right, so two ways. Raise your hand if you want to speak verbally, or type your question in if you want to use the Q&A box, and I will read it on your behalf, and we'll get Petter to answer. Okay, so again, for those that just joined in the last 30 seconds, we're going to make this interactive, either via voice or via typing the questions in. And with that having been said, I think I'm going to turn it over to you, Petter.
Thank you, Blaine. Yes, I'm Petter Graff. I'm the CTO of Pratexo, and have a very long background in building systems, both on the edge and in clouds and in various settings. And then I'm not going to go into all the details, because when you get to my age, it's going to take a very long time. So, but anyway, I've been working on these type of problems, particularly very large scale problem like smart cities, also in space and various other places to build out systems. And we had some ideas around how we could do this better, which we have put together into this startup we call Pratexo, when we were lucky enough to win the Edge Startup of the Year a few months ago, or a few weeks ago, actually. So we'll see. That's fresh off the press. Anyway, my email is in here if you want to reach out to me later as well. What I'm going to talk about is a little bit different maybe than what everyone else talks about when it comes to Edge. So this is probably a slightly more advanced topic than what you typically hear when people are talking about the edge. Most of the time when people are talking about the edge, they talk about being able to collect dark data, being able to process it close to the edge, and being able to transfer it up securely and so on. And all of those things are very important, and they enable business values in a lot of different verticals. But when you get a little bit mature on that, you might start looking into, can these edge nodes form a society, if you want, or what we call a cluster? Can we get these machines to collaborate? And that's what I want to talk about today, and what challenges you run into when you do that. There are a lot of challenges. I'll try to focus on a couple of them perhaps, and then I'll try to get questions from you guys, solicit some questions and see if I can answer those. So let's start with, what am I going to talk about? So I'm going to talk about what are some typical edge deployment, and how does that naturally evolve into the kind of things that I want to talk about, namely the clusters. So sort of from edge to cloud, how does data get transferred in our typical use cases? I want to talk about the ability of putting a set of machines together to solve some common good. Usually that is some kind of computational problem. So we usually call it a compute cluster. But it could also be for other reasons. We might want to store, for instance, replicate data across machines so that if one machine goes down, we are able to recover that information. And then I'm going to talk about something a little bit more dynamic and a little harder, actually, which is this concept of compute swarms. And for some reason, there we go. The Zoom bar is right in front of me, so I can't really see what's on the screen. So that was okay. I got it moved. So whenever you start building a system on the edge, maybe you have a set of sensors out there in the space. You have some goal, some business goal that you want to do, and somewhere between, the real world where you are able to either control or just read what's going on, and the operators that often sit somewhere else, you're trying to extract some value. And sometimes that is a blank canvas. And of course, as a system integrator or a builder of a system, that's awesome. Then you can use everything you have and put everything together. But sometimes there are some severe constraints in that space. And those constraints can be hardware related, network related, or there might be some kind of software constraint that you run into. Now, if we talk about hardware, that has a very important implication for your solutions. I've heard the concept of edge and fog and on-premise, public cloud. Those are very common places where we're able to run some software or do some work. I'm not too fond of these words because we quickly run out of watery things we can talk about, right? So we have solution spaces where we identify up to 12 of these different compute layers, 12 different places where you can do things. And what do you call them after you run out of edge and fog and cloud, right? What do you do now? But my point is in between the dashboard and your sensors, there are a set of places where you have the ability to install something. So on the edge, we often talk about computers like these type of computers, right? Industrial computers that we put out in the field that are sitting very close to the sensors. So those were most of the time we agree that those are the edge. But for instance, I do a lot of work for PayPal, and the edge for PayPal is their web browser. So it's really where we start getting data in, right? Fog, those kind of concepts are often about installing software maybe in a 5G station. 5G network providers are now looking into providing an availability zone for you where you can install software, or it could be some other physical location where you have the ability to install some hardware and therefore also install software. And people put things on the premise, and of course we have the public cloud. So you might have some constraints based on that. But when you look at what really happens, the software, what it has to do, it's fairly predictable, right? We collect the information at the edge. We typically have to canonicalize that information, meaning convert it into some form so that we don't have to speak 10 different protocols by the time we get and look at the data and analyze the data. There's usually some aggregation and filtering happening, meaning maybe the sensor is producing 100 readings a second, but we really only need the average per minute. Maybe there's a temperature or something like that, or there are certain values that is not of interest to us. So we can minimize the information that goes up, but you also have actions that we take. So those are usually called forward chaining rule systems. So when this happened, do this, and all of these things can happen anywhere, right? You can run it on the edge, you can run it in the fog, and so on. You have event stores and distribution that you can also put on the edge. You can put it in the fog, you put it in the application, and you have in on-premise, in the public cloud, and you have all your applications. And across all of this, you have this idea of observability, security, and traceability. But again, I'm not going to talk about those that much. But what I will talk about is how you can evolve from, for instance, looking at, let's say, the action here, not only from the perspective on a single location where you have an edge compute, but also start making decision that goes across multiple machines in various forms. So what can run on the edge is pretty much anything on that picture, right? So if you're putting out a computer like this one, these are fairly capable computers. They can easily run, you know, your database. They can run various applications. You can do forward chaining. We also have, of course, things like corals chips like this that you can put out on the edge. So you get TensorFlow on the edge, and there is really no limitation to what you could run on the edge, as long as the edge has what I call full event horizon, meaning it can see all the events it needs to see to be able to make the right decision. Things that are typically not deployed today are sort of critical persistent and event distribution and consumer application. And often that has to do with scale or replication of data to make sure that things are replicated. And that's when we often go to the cloud, right? So if you look at Microsoft's solutions or Amazon's solution, we're trying to push the data up to the cloud where we're using almost a transparent gateway, or there might be some rules done, but primarily event sort of creating canonical events from the sensor. We push it out to the cloud because there is where we have all this event stores and replication and so on. And then there are certain advantages to a solution like this. If this is your first taste of edge computing, it may have great advantages, right? You can take the dark data that often were sitting out in the field that you were not able to see, push it up to a cloud where you can process it. You have these highly available services available to you either through services of the edge or the cloud provider, or you can easily build your own. Now, there has been a trend towards pushing more of the processing down to the edge, and that's often to improve things like latency and being able to operate offline as well. But it has certain limitation. It typically doesn't give you high availability. So you get single points of failure. You might lose data if you do some kind of store and forward on the edge computer. You might lose the data. You might not be able to replicate information, but you will get some degree of offline capabilities, and you typically improve your latency. Now, the kind of solutions that we have come, or that we're trying to build, often involve a little bit more than that. Now, there are certain, if you have some form of fog layer, or you have some central node. So let me give you an example. Maybe you have maybe you have devices installed in every home that is doing local automation for energy consumption or energy savings and so on, right? And then maybe you have some transformer station where you can place another compute that can collect the data from the edge computer, make decision across those. So that is one possible way. And that gives you some multi-layer hierarchical deployment. And it does increase your event horizon, meaning you can look across more locations, but it doesn't really solve the high availability problem. And this is where the concept of a microcloud, or what we call a microcloud, comes in. And that allows me to have some lateral communication in addition to the functions that we typically see on the edge. And that means that every edge computer will be given another responsibility. And that responsibility is to be able to collaborate with others. And there are a couple of different variations of that I'll show you. There is the collaborative compute, and that, to be honest today, the best one of those are obviously Kubernetes, but you have things like Apache Spark that you could use and so on. And you can natively install something like Kafka to have a set of machines collaborate on doing some task. Now, this works pretty well in static or nearly static configurations. And I'll give you a couple of examples of that. And then for trivial, it may have some really trivial compute solutions. Like it could be as simple as I want to replicate my data across a set of nodes, which is, relatively easy to achieve today with tools such as Gluster, and there is a ton of other tools that would allow you to do that. But you can also want to create these more complex compute solution where your goal is maybe to deploy a massive job across a set of compute nodes. And Kubernetes is obviously one of them, which allows you to do things different ways. You have Apache Spark, as I said, Hadoop, other things. And then there is a fairly new strategy that has come over the last few years, I would say, at least become practical over the last few years, which is the dynamic configuration of compute resources, sort of ad hoc connection, a set of machines start collaborating, and they typically don't collaborate based on their network or some kind of static configuration. They collaborate maybe based on proximity, maybe based on some topics, not their physical address on the network. Here is an example of a cluster that we put together. This is for a power company in Norway. They have these transformer stations that you can see up on the right. So they're going to have about 3,000 of these transformer stations. And it has a set of PLCs, basically, that measure the quality of their service, the fluctuation of various parameters in their net. And the raw data was always collected, and there were certain decisions being made on the PLC, but it was always dark data. They were not able to take this data home. In other words, they were never able to look at this data, analyze it, or do anything with it. So what we did is we put a machine, you can't really see the machine in there, but there is a machine, a compute node that sits in each one of these transformer stations, now connected through Modbus to these PLCs, and there's a set of other sensors in there that we also talk to. And now we're able to collect that data. And yes, we can do the filtering, we can do the aggregation, we can do the local or the forward chaining rules, like if this value goes high, we can, if there are some actuators, we can do that. Like for instance, if the door goes up, we can turn on the lights. Let's just do something simple. Now the thing on the right here is on-prem and so on is from our configurator tool that allows us to draw this up, but it basically concept is that they have a set of machines on premise, and then they have a transformer edge, which is the one that gets installed out here. But then we have put together a Kubernetes cluster for them. And this allows us to put a set of tools onto the edge nodes, which are quite capable. They're quad core machines. They have 16 GB of RAM. They have a terabyte of disk space. So they're fairly potent machines. And we also, when the machine is out there, although this is a story for another day, it turned out that we asked the power company, okay, how do you actually figure out when a transformer needs service? And they said, well, we go out and listen to them, right? So we also put in a TensorFlow chip, or one of Google's Coral chips. So we're listening to the sound of the transformer and inferring whether something needs service. But and also the data is replicated, so they would never lose their critical data. After it's been processed locally, it gets stored into a Gluster file system, which means that it's replicated to their neighbor nodes. So if a machine goes down, for whatever reason, let's say one of these machines goes down, you can just swap it out, put another one in, and it will restore itself, and it will restore the state of the old machine. So as an end result, we're able to do this much more fancy streaming analytics directly on the machines where the data is collected at an enormous speed. So we're able to react to events that are happening in the net in near real time, even if the event horizon goes across all these nodes, right? So there might be some kind of rolling spike or so going on in the network. We can see that. We can also do forensic analysis. So our data is stored also in Elasticsearch that are replicated across these nodes. And we do the raw processing of that on Apache Spark. Now, if you look at this from the power company's perspective, they basically built themselves a fairly powerful data center, which is with an extremely high availability. Because how do you actually, or security, how do you actually take down a system that runs across 3,000 distributed nodes, right? I can't see how you would do it. Anyway, so if you look at it, each edge node has 16 gigabyte of RAM, 1 terabyte of storage, and a quad-core Intel CPUs. As an end result of that, they have 3 petabyte of storage. They have 48 terabyte of RAM and 12,000 CPUs to their disposal. So it's highly available, highly robust deployment. And of course, they save themselves a ton of money in cloud storage and cloud processing. But more interestingly is the extreme high availability of the whole cluster. Here's another use case where this became, which illustrate a couple of things. So this is for ships.
Better.
Set out the set of compute
We got
nodes.
one quick question about on the last use case. The
Yeah.
question was, you got 1 terabyte of storage. Is it SSD or regular HD? And if you have all these CPUs in an entire cluster, does that include computational storage CPUs? Is the question.
Yeah. So so all of the disks that we put in are SSD. 1 terabyte SSD is fairly cheap today. The computational storage, I'm not quite sure what we mean by that. So there is obviously a computational storage that is the intermediate result of computation, or things that help you towards a result of your computation. That is stored, and that is actually controlled by Apache Spark itself. So if you know how Apache Spark works, the Apache Spark has the ability to cache any intermediate result, any complex data structure that may be valuable for a next computation. So if that's what you meant, then yes, it also has the computational storage.
Thanks, Petter. Okay, keep rolling.
Okay. Another example was for ship. And here you can imagine the ship is, it has a lot of different areas where we have sensors. We have the machine room, which is obvious, but there is also these holding cells for containers, for instance. And maybe we're able to talk to those containers with various forms like LoRa sensors or things like that. You have the crew room that has need for certain computational tasks. And of course, you have the helm of the ship itself. So the idea is to put out a set of these nodes and network them. And now we have a computational cluster, basically a Kubernetes cluster on a ship. And another thing that comes into this play is the actual, when you start doing that, you can start talking to the vendors of democratizing the data. Let me give you an example of why that is important. We have a customer that is able to, if you give them the weather patterns and the RPM of the machinery and fuel consumption and so on, there's tons of sensors for that on the ship. They can save as much as 20% of the fuel cost. However, they never, because each one of the vendors that have this data has created their own isolated system on the ship. If you go into a helm, right, you will see all these monitors, and often these are completely independent vendors that all have their own sensors. But what we have tried to do for them is to say, no, let's create a democratized event stream of everything that coming from your sensors, and make sure that you as a ship owner can control which systems run these, which system can have access to what data on the ship. So you can actually have, the ability to deploy an application without having to go and drag new wires, which is extremely expensive on the ship. In fact, for this customer, the software itself is cheap, but the installation averages, I think, almost $50,000 per ship, because they have to go and build new sensors where sensors actually exist, and data is collected and pushed to the helm, but they do not get access to it. But the end point here is that you have a set of these machines. They're spread out in the boat. If one of the machine goes down, we do not lose the ability to do the compute work and so on. We just lose capacity, right? So there's this saying in big data there's two sayings in big data. One is, don't send your petabyte to your algorithm, send your algorithm to the petabyte. In other words, we can send an algorithm from shore to the ship. And obviously that has a dramatic effect, because the cost of communicating while you're at sea is extremely high. So if we can send down a job, if you want, that is looking for certain information that has a result, like how much fuel have we used? How much fuel do you think we need when we dock in New York, right? Or how much space will be left, whatever it is. You can send the algorithm, which is very small, to the ship and have it calculate the result locally, and then send the result back to shore. So that's one of the things. The other saying in big data or sort of highly available clusters is, do not install pets, only install cattle. Meaning, if one of these machines goes down, we lose a percentage of our capacity and not the integrity of the cluster, if you want. We have another use case for smart building, also fairly static solution, where we could have, for instance, a machine sitting with every tenant that is doing local control of their air condition, lighting, and so on. We can democratize the sensor data so that various applications get access to that sensor data. So for instance, a movement sensor may at day act as a light switch, right? But at night, it may be an intrusion detection. So anyway, so that's another example of a place where those kind of solutions fit in really well. The other form of clustering is what we call swarms, right? And swarms is a bit different, because the configuration is not static. So I'll give you an example of a swarm as well. So this is an example for threat detection on military vehicle. And let's say they're all lined up and they're driving together on some road. The front vehicle here has a view towards the road, and there are algorithms that one could deploy that is looking for signs of, say, an IED or any kind of threats in front of you. You also have to look to the side and upwards and towards the tail of this fleet of vehicles. So what we can do is we can put a machine on every node that has the ability to do, simple machine learn or classification over images. But what we can do is we can have all these machines collaborate. Who's in the front? Because those pictures are the most important. Obviously, we want to look for IED in front of the vehicle. And then we can have all the other cars make up an ad hoc compute swarm to help analyze the images that are coming in. So, every machine, every vehicle has the ability to look at the cameras and do some inference, but for very high inference, maybe for with the creation of super resolution and so on, you can delegate some of the computational job to the other vehicles. So as an end result, we get sort of a 2 orders of magnitude in a typical large fleet. We would have 2 orders of magnitude better performance for the critical scenarios when there are things in front of you. And of course, it's also highly fault tolerant. If one of the vehicles loses its ability to see, camera goes out, the machine burns up, whatever it is, you can easily swap them around, right? You can make another vehicle do the job in front or drive in front. Here is another use case that I really like, and this is bird detection on a windmill, where so there are, by regulation in Europe, you cannot install a windmill unless you know what impact that has on the bird life. And the solution prior to Pratexo was a very high resolution camera that would be looking typically these windmills are put in clusters as well, so they may be looking at the windmill across the sea. In Norway, they've started doing these floating windmills in the North Sea, and then they have a compute cluster or a massive compute machine that sits in the root of the windmill itself, or in the I guess the foot of the windmill. And often, because you're looking at a very large distance, you only have a few pixels, as kind of shown on the right here, of that you're trying to recognize. And the cameras here are, as I said, extremely expensive. The compute cluster is really expensive. But what if you do this a little bit different? I can't show you the pictures of the birds yet because we're still working on the solution, but the idea is to have many cheap cameras with telephoto lens, right? In fact, we figured we could have somewhere in the order of 1,000 of those for this one big camera. And each one of those will be equipped with, a TensorFlow, a machine learning compute node, and they all are looking at a small piece of the sky. We can also have them overlap so they look at the same piece of the sky to create what's called super resolution. But this is tricky, right? You have to have these machines kind of collaborate. When did you take that picture? What direction did you point when you took that picture? And also we need to know that, oh, we lost sight. Maybe one of the machine went down, one of the camera went down, so we lost the ability to see in a certain direction. To adjust the algorithm, because some of these algorithms can be based on statistics and so on. Now, this bottom line here is basically just an example of a super resolution algorithm where the actual picture, there are several of them that looks at what at the left, but by using the super resolution algorithm, we can kind of enhance it to what you see on the right. It's used a lot in space, but it is also used for medical imaging, for looking for cancers and bacteria or viruses and so on. So but now we can start using this. But the trick is, how do you get all these machines to collaborate? How do they get to work together? And that's where these swarm algorithms come into play. So the point here is there are different modes of deployment. You have sort of the standalone edge computing, if you want, where we're trying to get the data up into the cloud, maybe via some intermediary, like what we call fog compute, to improve on the event horizon, if nothing else. And this gives you security and latency and privacy, and the data becomes visible. And then we have this concept of distributed edge computing, where you have a relatively static configuration of nodes. What I mean by relatively static is that the machine would at least participate for an hour or so before it's worth doing this, because there's often some cost involved with tearing down a node and bringing it back up. But that gives you reliability, scalability, availability, and so on. And then we have this concept of swarm edge computing that allows me to open up a set of new use cases, and it gives me some flexibility and efficiency. Now, it's a little bit more tricky in those cases to get reliability, scalability, and availability, but it is possible. When we go into this space, there are a set of challenges. And honestly, whenever we hire someone and bring them in, we spend weeks on training them on all these challenges, because it turns out to be a little bit tricky. Maybe the biggest thing is to most of the engineers, software engineers that are going out even on the edge, have no concept, or they have not been working with distributed computing. So this knowledge is very sparse, and some of the architectural patterns are not common. There are some unique challenges also for the type of clusters. The compute cluster, the network configuration that we see at our client side could be quite challenging to get a Kubernetes network, for instance, to work, which is used to running in a data center with all kinds of redundancy on networking and so on. So the fact that the node goes down isn't necessarily a big deal when you're on the edge. It may be that we have an unreliable network. So we need to make sure we use distributions of Kubernetes where that is possible. And there are a few of those available today, like Micro K8 is pretty good, K3 is pretty good, KubeEdge, there are other out there as well. And the installation and patching of cluster software in disconnected environment is also tricky. So most of these deployments assume that you can, for instance, reach your Docker hub or reach, you know, your Snap repo, or whatever it is that they assume. But in many cases where we work, you're disconnected from the network where you install a node. So we've had to solve that as well. The swarms is also a bit challenging. There is a lot of logic that we have to take into account, and we have to create our models based on physics, not mathematics. So what does that mean? So in computer science, you know, it was heavily influenced by Eddie Dijkstra at the University of Texas and his models of how we go about proving that our computer algorithms work and so on. They just don't work in a distributed environment on the edge. So you have to base it on physics. And there were other computer scientists that were on that path, maybe predominantly Carl Hewitt with his active model and so on. You have to think a little bit different. And just to dig into a couple of these, I'll just give you sort of a brief idea of the kind of things that we train our engineers on to make sure that they, or our system integrators on. So for instance, take the simple thing like distributed, well, not a simple thing, but an example of a challenge, distributed computing. So every developer sort of worked with the assumption that they run on a single machine. Many of the framework, let's say a web service framework or microservice, assumes that you get you're the one that handles this request, and you're the only one that handles this request. But in a edge compute world, when you start putting together cluster, you have to understand that you're going to collaborate with others to do this. And some knowledge that come in handy here is, you know, things like mapped concept from the topic of category theory, at least sort of understand the concept of a monoid, a monad, semi-groups, what are their properties, how do they work, how do they help you. You also have the CAP theorem. So often particularly when you deploy a cluster, you might be using one of the open source tools, let's say MongoDB, Kafka, CouchDB, Cassandra, you know, whatever tool you pick, you have to know that these tools have certain properties. They're optimized for a particular type of deployment, and therefore you have to take advantage of that. And there are all these scalable architectures that aren't necessarily known, like Lambda architecture, event sourcing, distributed stream processing, and how you do that, CQRS, actor models. And let me just dig into the idea of monoid. So just as an example, let me just walk you through what a monoid is. Why is it important? So this is Moore's law, which I'm sure everyone has seen. And what I want you to take a notice of is that the flattening of the clock speed. The individual cores did not get any faster than what they were in around 2000. And I can go into the physics of that, but the point here is the way we scale, even on individual computers, is by adding more cores to a problem. More cores mean parallelization. Okay, so as you add more CPUs to a problem, you would ideally like to see a linear curve, right? The more CPUs, the more core you put onto a problem, the better the performance. But that's not what you're going to observe. You're going to run into what's called Amdahls Law, And that's I mean, I can explain this in details, but I'll let you guys look it up if you're not familiar with it. But it's basically the whole idea is you cannot improve your performance by adding more cores or more processor or more machine to a problem beyond how well you have managed to organize your algorithm for parallelism. So what Amdahl is saying is you're going to eventually hit a ceiling, and that ceiling is based on how much you can parallelize. It's a pretty obvious law, but because we only have 20 minutes left, I'm going to skip ahead. And it's the truth is actually quite a bit worse. So Ginter in 1993 wrote what we often now call the Ginters Law, or the universal law of computational scalability. And he basically just pointed out that as you distribute, you will have a cost of distribution. Therefore, you would always hit the local maximum. There is a point in time when adding more cores is actually going to slow things down. So you have to find algorithms that actually work. And this is just one of these problems. So in category theory, there is this concept of what we call a monoid. There is also monad, which is actually the more practical of them in computer science, but I just want to show monoid because those are easier to explain. There is this thing called a monad curse, where they say that if you ever understand monads, you immediately lose the ability to explain it to someone else. But basically, if you could look in Wikipedia, you see that a monoid is an algebraic structure, a set of values, if you want, with a single associative binary operation and an identity element. Meaning, a binary operation means you have two values, right? You apply the operation and you get one value out of it. It's associative, which means if you have A and then the operation B, operation C. So as you chain them together, you can do A and B first, and then take the result of that and apply it with B and C, or you can do it the other way around. You can start with A and let B and C run separately. And then identity element means that there has to be a value, an identity value, that if you apply it on the left side or right side of the operator, it will have no effect. So if you look at something like addition, adding numbers up, that's fine. It's a binary operation, is associative, and the identity element is 0. But I said subtraction, and then I changed it to division. But a division is not, for instance. There are no identity element, and if I do 8 divided by the division of 2 on 2, right, I get 8, but if I do it the other way, I get 2, so it's not associative. But things like list concatenation, for instance, is. So when you have a monoid, then developers will still do the mistake of writing algorithms that are in mathematics called leftfold, meaning they do something like this. You start with the sum equals 0, and then for each one of the values you add so you start with the identity and then you add on the values. But the problem with this is that it's a sequential algorithm. It doesn't have any parallelism. So basically when you do this, you will pick one core and you would pin that core, but you will not utilize any other cores. Or if you did it in a distributed environment, you would have one machine do the work and the rest of them would have nothing to do. But if you know that this operation is a monoid, you can easily parallelize it, right? Because it's associative. You could do 1 and 2 in one CPU and 3 and 4 in another CPU. They reduce, and then you could do the addition of that in the third CPU. So what I often do for large corporations to help them scale is that I have to go in and look at their algorithms and convert them into a monoid, and this conversion into a monoid and back and get this what we call monads. Another thing is, as you get these clusters, you're going to pick these different tools. And when I go out and ask someone, okay, which tool did you pick? Oh, I picked MongoDB, and ask why. And one good reason might be their documents, their data is documents, but there is another one here, like CouchDB, also store documents. So why would you pick one or the other? Well, there are two completely different tools to us, right? One is a tool that focuses on consistency. and therefore sacrifices availability. And if you want to know why, you should read Eric Brewer's PhD thesis, which is the origination of the CAP theorem. But basically, you can, if you partition your data, which you will do when you go distributed, you have to pick between consistency and availability. You can never get both, right? But just knowing where your tool fit in this is another one of these challenges. Now, I'm going to leave the rest of the time for questions. So let me just summarize this. So we believe that the use of collaborative edge computing is an underutilized concept in the solution spaces where we operate. Edge-based compute clusters bring the advantage of the cloud to the edge if you want, so you can get high utilization of the hardware, highly available software solution, and sometimes dramatic reduction of cost. The edge-based sort of swarm computing is a little bit newer. It's much more elegant, and we have observed up to 2 orders of magnitude better performance in some use cases over what you would get for more static configuration. And then I also want to point out that clusters, building cluster on the edge introduces a set of new challenges, so just be aware of the learning curve. I just picked one of those, right? Distributed computing, well, a little bit of CAP theorem too, but and there are several others that you need to be aware of. So just be aware of the fact that if you have not been working in that space, there is a learning curve. Okay,
thank you,
Blaine,
Petter.
over to you.
Yeah, we do have a couple of questions here, and while we're answering those, I request others feel free to enter your questions in. Not every day you're going to get a chance to ask Professor Graff questions about distributed and swarm computing on the far edge. Trust me, so there's a good opportunity, and I know we've got quite an audience here. So one question from Stuart was around, is it possible for edge nodes to be able to dynamically switch from one cluster to another? You talked about how these can be clustered into sets. Can they be dynamically allocated between clusters?
Yes, and in fact, there are use cases in which they may participate in multiple clusters, right? So the clusters tend to be topical. So imagine, for instance, that you have an edge node sitting in a car. They may be collaborating with other cars that are on the same road segment to inform them about, road conditions, traffic, things like that, right? But they may also be collaborating with a set of friends on another cluster. So these are dynamic concepts. So think of the swarm participation as a role that the edge node can play, and it can play n number of those roles. And there is an open source tool that I created once called Yactor. It's been laying kind of dormant for a while, but we're bringing it back in with Pratexo because it turns out to be a really, really good way of thinking about swarm. And that is a system that I built, and I had to open source it because I was working on the smart city of Denver, and that was sort of the foundation for that. But that allows you to put together different roles, and each one of the edge nodes in this case may participate in a myriad of different swarms, right? Okay, yeah, a good question.
Yeah, thanks. Yeah. Let's see. Another question was, you haven't really talked much about Pratexo itself in this, and the question was, how does Pratexo actually make setting up these systems easier? So
Yeah, so what we have is what we call a configurator. And I could show that really quick. Let me just log into one here, and let me open up an example. Let's take the power company, for instance. So this is the power company cluster. And you see here, one of the things we do is we allow an architect to kind of draw these things and configure, the edge nodes, what should run on the edge node, what is the cluster, what style of cluster do you have? Is it a parent-child or a swarm cluster, right? And so on. So we allow you to configure this up. There's still work that has to be done by you, but we're trying to help you with everything from the install to definition of those clusters and so on, right? And then when you process this, we generate all the install scripts and documentation and simulation of those clusters, so you have some place to run it and so on. And then, of course, we're trying to help our customers. I think over time, we're hoping to entice all the system integrators there to do that job for us. But right now, we're also being consultants, I think, when it comes to these solutions. Yeah.
Excellent. Thank you for that brief intro. And obviously, we and you would be happy to dive deeper into Pratexo at any point in time if somebody wants to reach out. We got another question here on the direct chat channel to me, which is, are there any use cases related to swarm computing on the edge of space? You mentioned space earlier.
Yeah, actually, I'm not sure if I can talk about that one, but yes, I think, I mean, the short answer would be yes. And we are actually involved with 2 different things in space. And yeah, clearly that is in space. And, you know, there are one that deals with sort of autonomous spacecraft and collaboration between those spacecraft. And there's another one that I know I can't talk about. So, but the short answer is yes. And I think your imagination will probably be able to come up with good reasons for that to work, right?
Okay.
Even
right.
we'll
use our imagination. Yeah, that's good. All right, David asked us, it's a good question, a fairly lengthy question. So get ready, Petter.
Yeah.
And I think it's relevant. So looking at clusters on the edge and taking into consideration more operations or business value, can we connect this discussion to how edge clusters could follow mobile users in a home, travel, or office environment? All right.
Yeah, so
maybe I'll leave it at there. Yeah.
Yeah, no, that's a great question. I think swarms are actually better candidates for that because they would kind of dynamically follow you. So we're working on a solution now where, imagine in that smart building that you can then connect to occupants in the building. So we can use their cell phone, for instance, to make up a compute cluster. And it can be something like, imagine a conference, right? Where you deploy an app where the conference participants swarm together, sort of a birds of feather solution. Now, there might be also one thing I should point out here is swarm and compute clusters are not mutually exclusive, right? So you could have a swarm or a compute cluster participate in the swarm, be one of the participants in the swarm, maybe the one that sets up the main topics and so on. So these are not mutually exclusive. But yes, in particular, when it comes to this type of mobile application where things are moving around, swarm is, I think, a better answer, but a more tricky answer than the compute cluster. Now, most of the compute clusters today, and that might change over time, originates from data centers where the configuration is relatively static. And it's not like machine comes in and out all that often. So they tend to be a little impractical for that right now. But we try to combine the two, right? So we have solution where swarm and compute clusters live not side by side even, but they collaborate.
Thank you, Petter. And why don't you go back to the home, your initial starting slide to put up the contact info there. Let's go back up to the top. Get your email address and my email address as well. I think this has been a very interesting 55 minutes or so. You can see the contact info for Petter and myself there. Of course, if you'd like to speak to us more about edge computing, swarm computing, distributed computing at the edge, obviously, we've got one of the experts on that topic, and the expert, I would say, honestly, is our CTO and founder of Pratexo. And the Pratexo platform is fundamentally about making it much more quick and easy to stand up and maintain these kind of systems going forward. So if you'd like more information on that or any of the topics we covered today, please reach out to us at the contact info there. Check us out at pratexo.com, and we'll be talking to you.
Thank you, Blaine. Thank you, everyone.